Hey guys, it's me again, talking about probability this time. Um, this may sound more like a math class for this section, but you'll see how it ties into biology soon enough. A little cartoon here I thought was kind of funny. Maybe not. Anyway, you're probably wondering, or know, what is probability? So, probability is basically a mathematical tool used to predict the likelihood of events in everyday life. Sorry, hold on, let's stop. There, I think I resized the screen so it can all fit. But it's basically the expected frequency of some particular event when an experiment is repeated an infinite number of times. That is basically the probability of an event. Um, when we're talking about genetics, it's often used to predict a certain hypotheses, and then we can test that hypothesis using real data. And that's what Mendel did a ton. He actually did this with pea plants. He predicted the outcomes for pea plant crosses, and then over thousands of generations and the course of 8 years, he was able to statistically analyze the probability of certain events. So, for example, here shows you that he crossed smooth seeds with wrinkled seeds almost 8,000 times, and he got this many smooth and this many wrinkled. And so he basically said, look, it's a 2.96 to 1 ratio, which is pretty close to a 3 to 1 ratio. And then I did this 8,000 times, and this is how many times I got it. So he was able to average those out and figure out the probability of certain events. So probability is the number of times an event is expected to happen divided by the number of opportunities or trials that are done. So it's usually expressed in a fraction, although sometimes it's in a ratio. So here's an example. Say we were wondering what the chance of landing heads being up in 2 coin tosses. We would say that that's 1 out of 2 or 1/2. The chance of drawing an ace out of a deck of cards is 4 out of 52 or 1/13. And it can be explained as a percentage. So there's a 50% chance of a coin landing heads up when you toss it. There's a 7.7% chance of picking an ace up from a deck of cards. And we can use the principles of probability to predict the outcomes of a genetic cross. So we can try to figure out the ways that alleles are going to segregate. And we need to remember that Mendel's rule of segregation is that those alleles segregate independently of each other, just like flipping a coin. So here is a purple pea plant that's heterozygous, and when it makes its alleles, the sperm cells or the egg cells, there's an equal chance, if it's heterozygous, for a big P, the dominant allele to be in one, or the recessive allele. So again, remember that principle of segregation, that genes come in pairs and they separate in the formation of sex cells, and those sex cells unite randomly in fertilization later on. But how they segregate is totally independent of all the other genes. So I like this picture because it kind of shows, okay, let's say we go back to those purple plants. Here's a dominant allele, here's a recessive allele. We could put them on the sides of a coin and flip them, and that'll show you the likelihood of getting each of the allele combinations. Cystic fibrosis is an autosomal recessive disorder, so it's a disease that's the only way to have it is to have 2 recessive alleles, and it's carried on an autosome, so not a sex chromosome. So a man and a woman are both carriers for cystic fibrosis. What are the chances of them having a child with the disorder? Well, we can make a Punnett square, which doesn't show up there very well, and this is their allele combination. Notice I didn't use C's here because a capital C and a lowercase c look kind of similar, so I used the F's. So they're both carriers, and we can check out the Punnett square. There's a 25% chance that they would have a totally normal homozygous dominant child. There's a 50% chance that they'd have a child that's also a carrier, and then there's a 25% chance that their child would have cystic fibrosis. So I want to talk to you guys about 3 major rules of probability, and if you know these, you can understand a lot. The first rule of probability is kind of obvious, but a lot of people get confused here. The gist of it is that the results of one chance event really have no effect on the results of subsequent chance events. For example, my cousin already has 3 boys and his wife is pregnant. What's the probability of his 4th child being a boy? Well, you would think that there's, you know, since he already has 3 boys, he's unlikely to have a 4th boy, but each separate event, it has its own probability, so it's still going to be 1/2 or 50% chance. Another example, if my college roommate Victoria and her husband Peter are carriers of cystic fibrosis and have already had a son with the disorder, what are the chances of having another child with the disorder? Well, again, if you did a Punnett square, you would see that there's a 25% chance with each pregnancy to have it. So there should only be a 25% chance with each pregnancy. 2 other rules of probability you'll need to understand. The first is the rule of multiplication, and this is that the probability of a compound event is equal to the product of the separate probabilities of the independent single events. I know, that's kind of a mouthful. But basically, the probability of event A and B happening is the probability of event A times the probability of event B. So, what's the probability of flipping a coin and getting 2 tails in a row? Well, we take the probability of the first penny being tails. We multiply it by the probability of the second coin being tails, and that equals the probability of getting both tails on both pennies. So 1/2 times 1/2 is a quarter. The rule of addition is the probability of an event that can occur in 2 or more alternative ways. It's equal to the separate probabilities of the different ways. So what's the probability of a flipping 1 head and 1 tail in a toss with 2 coins? Well, you could get the first penny having heads and the second penny having tails. Wait, let me say that again. The probability of flipping tails on the first penny and heads on the second is 1/2 times 1/2, and you're gonna, which is equal to a quarter. And you're gonna add that to the probability of having heads on the first penny and tails on the second penny, and that's gonna be equal to the probability of getting 1 tail and 1 head in a toss. You could also do the same with what's the probability of having 1 boy and 1 girl if a couple has 2 kids. Well, it's the probability of having a boy first and then a girl, plus the probability of having a girl first and then a boy. So here's another practice problem. What's the probability of any couple having 4 boys in a row? Well, that's going to be 1/2 times 1/2 times 1/2 times 1/2, or 1/16, 6.25%. What's the probability of my friend Victoria and her husband having 2 kids with cystic fibrosis? Again, we're going to take the probability of the first event, multiply it by the probability of the second, and that should be 1/16. So, is the following sentence true or false? Just a little trick. The past outcomes of coin flips greatly affect the outcomes of future coin flips. Oh, that's false, right? Yeah. How can you be sure of getting the expected 50-50 ratio of flipping a coin? Well, you got to flip that coin a lot of times. In fact, the more times you can flip it, the closer you'll come to your expected outcome. So the larger the number of offspring from a genetic cross, the closer the resulting numbers will get to the expected values. So sure, my cousin has 4 boys, or some people have 5 boys, but if they had an infinite number of children, they should have half boys and half girls. So what works for peas also works for humans. Albinism is an autosomal recessive condition. In order to show the disorder, you have to have 2 recessive alleles. If you look at this Punnett square right there, you can see some of the outcomes. So here's a mom who's heterozygous, homozygous dominant, so she doesn't have it. Here's a dad who doesn't have it, and there's no chance of them having a kid who has it. Here's a mom who doesn't have it, isn't a carrier, but here's a dad who's a carrier. They still don't have any kids who have albinism. However, if a carrier of albinism guy marries a woman who's a carrier, then they have a 25% chance of having a kid with albinism. So that's it for notes. We're going to do the coin lab in class on Friday, so we're going to change that up. Do read about binomial expansions, and we will talk about the chi-square test in class on Friday. Thanks for listening. Have a great day.